Every time you write new in Java, an object is created and memory is used up. But who frees that memory? You never call free yourself. Instead, a background daemon, the garbage collector, prowls the heap and kicks out objects that nothing points to anymore. Think of it as a friendly monster that eats your unused objects. Let's watch it work. First, what is garbage collection? In languages like C, you allocate memory and must free it by hand. Forget, and you leak. Free twice, and you crash. Java takes that burden away. You just create objects and stop using them. And the garbage collector automatically reclaims the memory. That's automatic memory management. Why do we need it? Because manual memory management is error prone. The collector runs as a low priority daemon thread in the background, finds objects that are no longer reachable, and kicks them out, preventing dangling pointers and most leaks with almost no effort from you. So when exactly is an object garbage? Starting from the GC roots, things like local variables on the stack and static fields, the collector marks everything it can reach as live. Those get a check mark. Anything it cannot reach is unreachable, and that is the garbage the daemon will remove. For example, set a reference to null, and the object it pointed to may become unreachable. The instant nothing can reach it, it becomes eligible for collection, and the monster targets it to kick out. Where does all this happen? The heap is divided into generations. There's the young generation, the old generation, and a separate area called metaspace. Splitting memory this way lets the collector work smartly because most objects die young. The young generation has 3 parts: Eden, where brand new objects are born, and 2 small survivor spaces, S0 and S1. Almost all objects are created in Eden, and most die there quickly. The old generation, also called tenured, holds long-lived objects that have survived many collections, and metaspace stores class metadata. It lives off heap and replaced the old permgen back in Java 8. Now let's watch the collections, starting with a minor GC. As your program runs, Eden fills up with new objects. When it's full, a minor GC fires. It collects only the young generation, and it happens often. Step 1 is mark. Starting from the GC roots, the collector marks every object it can still reach in the young generation. These get a check, they're alive. Everything left unmarked is garbage. Step 2 is sweep. The daemon monster goes in and kicks out every unreachable object from Eden, reclaiming their memory in one shot. Then the survivors are copied into a survivor space and their age is bumped and Eden is wiped clean. Because a minor GC copies only the living objects to a fresh space, it compacts as it goes, no fragmentation, and it's very fast. Survivors that get old enough are promoted into the old generation. Over time, promotion fills the old generation. When it gets full, a major GC runs. It collects the old generation, and because old objects are long-lived, it's rarer but slower than a minor GC. Same idea, mark the reachable objects in the old gen, then the daemon kicks the unreachable ones out. But here, sweeping leaves gaps between the survivors. So the old generation uses mark, sweep, and compact. After sweeping, free memory is fragmented into holes. Compaction slides the surviving objects together into one contiguous block, so a big new object can fit and allocation stays fast. Moving objects costs a little, but it pays off in defragmented fast memory. The heaviest collection is a full GC. It collects the entire heap at once, young generation, old generation, and metaspace together. It usually runs when memory is under real pressure, or if code explicitly calls system.gc. A full GC is a stop-the-world event. Every application thread is frozen while the daemon marks and kicks out garbage across the whole heap. That pause is exactly why you want full GCs to be rare. Finally, it compacts the whole heap, defragmenting everything. It's the most thorough collection and the most expensive. Tuning a JVM is largely about keeping these full GCs infrequent and short. Let's compare the 3. A minor GC collects the young generation, runs frequently, and is short. A major GC collects the old generation, runs less often, and takes longer. A full GC collects the entire heap, is rare, and causes the longest stop-the-world pause. Minor GC uses a fast copying collector, major and full use mark, sweep, and compact. Java doesn't have just one collector, it has several. Serial uses a single thread. Parallel uses many threads for throughput. CMS was a low-pause concurrent collector, now deprecated. G1 garbage first is region-based and the default since Java 9. And ZGC and Shenandoah give sub-millisecond pauses on very large heaps. So which one, when? Use serial for tiny apps on a single core. Use parallel for maximum throughput in batch jobs. Use G1 as the balanced default. and use ZGC or Shenandoah when you need ultra-low pause times on huge heaps. Now a surprise. You can still leak memory even with a garbage collector. The GC only frees objects that are unreachable. If something is still reachable but you never use it again, the collector can't touch it. Common causes are static collections that keep growing, listeners you never remove, unbounded caches, and thread locals. To avoid leaks, you manage your references. Drop them when you're done. Use weak or soft references for caches. Remove listeners. Bound your caches with eviction and close resources with try with resources. When in doubt, profile with a heap dump. Putting it together, garbage collection automatically reclaims unreachable objects. The heap is generational. A minor GC copies young survivors. A major GC mark sweep compacts the old gene. A full GC does the whole heap. You pick a collector by latency and heap size, and you avoid leaks by managing your references. Interview round. What is garbage collection and why do we need it? It's automatic memory management. A daemon thread reclaims the heap memory of objects no longer reachable from the GC routes, freeing you from manual free and eliminating dangling pointers and most leaks. Walk through the generations. New objects go in Eden. A minor GC copies survivors into a survivor space and ages them. After the tenuring threshold, they're promoted to the old generation. Meta space, off heap, holds class metadata and replaced permgen in Java 8. Minor versus major versus full GC. A minor GC collects only the young generation with a fast copying collector. A major GC collects the old generation using mark sweep compact. A full GC collects the entire heap, including metaspace, and causes the longest stop the world pause. Explain mark, sweep, and compact. Mark every object reachable from the roots. Sweep away the unmarked ones, then compact the survivors together so free memory is contiguous, which prevents fragmentation and keeps allocation fast. Can you still leak memory with a GC? Yes. The collector only frees unreachable objects, so anything still reachable but unused leaks, static collections, listeners, caches, thread locals. Fix it with weak references, eviction, removing listeners, and closing resources. Now it's your turn. Take the topic test and lock it in. 10 multiple choice plus 10 short answers graded by AI. The link is in the description below. And here's something special. Top the leaderboard on 5 topics in a row, and you'll get a surprise gift from me, plus a personal one-on-one connect.